Hi everybody, it's AJ here again, and what's Gucci? I forgot to say that. And today I want to be talking about caching. And caching is a way to essentially use data, use fast memory in computers. Now, in a perfect world, every computer scientist or anyone who uses a computer wants there to be fast memory, also known as RAM, which stands for random access memory, for everything. But in short, RAM, random access memory, costs a lot more than regular memory, than disk memory. And because of that, most systems cannot afford to have all of their memory on RAM. So to change this, or make this more accessible, so the most memory possible is on RAM, they developed a system called caching, and caching allows you to store the most used data or keep track of the most recently used data in cache. Now, all your data needs to be in the cache to reference it from the processor level. And what I mean is, I want to start everyone out with an image here, and the image is that, imagine you're in a library. And this library has a huge amount of books, and you're sitting at your desk, and you're doing research on a topic, any topic, Pokemon, Yu-Gi-Oh, whatever you want, video games, and you have a few books in front of you, and you're studying all these books, and most of these books have all the information you need. But let's say you need a book to figure out, I don't know, you needed another encyclopedia to figure out something more. Well, for you to do that, you'd have to get up from your desk, get a book from the shelf, and bring it back. Well, that notion, what we're going to do is we're going to think about the desk as your cache, and going up and getting to the library, going to the library, going to the shelf, is accessing memory, is accessing disk memory. And getting up, that is a much slower process than just reaching on your desk and picking up that book and starting to flip the pages and reading that one. So the really good way to think about this is that every computer has a memory hierarchy, and that in a memory hierarchy we have RAM at the top, and then we have bigger but slower storages of memory at the bottom, and all of these storages contain what's above them. So, for instance, there are other sectors of memory which really you can look up, but we don't really need to go over. And then we can say this is the disk, and then every section above it is a little bit faster, and it stays there to communicate with the RAM, and the RAM communicates with the processor, which initially gets all the instructions for you to communicate on your computer. Now, the cache is developed into a few systems. The first kind of mapping in a cache is the direct map system. And so what the direct map system does is that when I need an address in memory, I'm given a byte address. Let's say, for instance, I'm giving a 32-byte address. So I'm given, whatever, a lot of numbers up to 32. And basically that tells me an address in memory that I need access to. And so what I'm going to do, what the purpose of the cache is that it keeps track of something called temporal locality. And temporal locality means that most of the times in programming, when you access something once, there's a very good chance that you'll be accessing again. For instance, if you're doing a loop through anything, you're going to be accessing updating your variables to update with the loop. So if you have a for loop and you're using I as your initializer, you're always going to be updating I or checking I against something. So you're going to be accessing that. That'd be an example of temporal locality. So when I have this address that I get up here, I can look up. What I'm going to do is I have certain ways to spread out this address, and my cache system works basically in three systems. So the first part, the leftmost part of these addresses that I get are my tag number, and the second block are my number of sets I have. And the number of sets I have, I'll show an example shortly, is the main communication, and then the other bytes I have, the remaining first bytes, are my bit offsets. So that's exactly the block I'm going to communicate. So what I'm going to do here is that I get this address, and that could have, you know, for instance, in this case, I'll just do 0110, 010, and then 11. And then so the sets tells me which set I'm going to look in, and then the tag number tells me if this is the correct address. And so I'll show an example. And so we can think of my cache as this little 8-box field that I drew above here. This is my cache, and each block, each row in this cache is going to store a block of information. A block of information is defined by the caches. It's defined as a certain length. So it could be 1 byte, it could be 10 bytes, it could be several bytes. It's just depending on how much the cache is going to store. And so what I do here is that I'm going to upload a set. And so actually, for instance, I know that, oh, this is the byte offset, not the bit offset, sorry guys. I know that each cache block or each cache slot can hold 4 bytes because of the 2 bytes I do to my example. So it can be at position 0, 1, 2, or 3 because 2 bytes can represent up to 4 numbers. And then I'm going to have a certain amount of sets, and then my tag number I'm going to show you is going to identify something that I will show you guys later. So I can have up to 8 sets, which is what I have here, and then I'm going to have a tag number. So what I do now is so if I have this number, I look at the set first, and let me number this off 0 through 7. And I guess we'll get rid of them. We can X out the last one. You know, I'll just include 8. We don't need 8, but we'll have it in this one because I just have 7 slots, and I have 0 through 7. So I actually have 9 slots, but I only need 8. So what I'm going to do here is I have sets, and this represents the number 2 in binary, 0, 1, 0. So I'm going to look at slot 2. I'm going to see if anything is in there, and nothing is in there. So what I do is I put this memory block in there. So I'm going to put 0, 1, 1, 1, 0, 0, 1, 0, 1, 1. So that block is in there in the cache. So anytime I need that block, I can, if I need that block, I'm going to look at my set number and say, okay, hey, my set number is 2. Is this set number in here? And then I'm going to say, okay, that address is in here, and then I'm going to get it from a cache. I'm not going to have to reach the disk thing. The whole point of the cache is to prevent disk going to the disk, going to the memory disk. And because if you have to go to the memory disk, that takes a lot more time and is very unreliable. And it wastes a lot more time. It's much more wasteful. It's like getting up to go to the library. And so, but what happens now? So let's say I add something. Let's say I change the tag number. This is what I want to show. So I have the same set and the same byte offset. Actually, the byte offset never matters. You're never going to compare it in the cache, but I'll show you guys. So I changed my tag number. I'm going to add this number to my cache, or I'm going to go to disk. So I look at my sets. What I'm going to do here is that I look at my sets, then I go here to my tag number, and the set tells me to go to 2 right here, so I'm at 2 again. And then actually what I do here is that every time I go to the set, I compare the tag number and the tag number, and the tag number tells me, I look at the tag numbers, and the tag number tells me if these are indeed in the same. I now know they're in the same set, but I don't know if they're in the same tag, and they have to be in the same tag for it to be a match. And so since they're not in the same tag, I know that, for instance, this is not what I'm looking for. But this cache is only reserved for sets that are 2. So I'm going to now replace this set with the one I'm adding in right now, because that's the one I need in my cache, and dispose of dispose of the other memory block that I got that was recently there. And if I change that memory block that I recently had, I'm going to write it back to the disk, because I need to write that change back to the disk so it reflects it if I have to get it again, so the changes are kept. So I have that. So now I have that. So that's a possibility. So what you want to do is you want to look at the set numbers. The set numbers can correspond to which blocks you can store it on in the cache, and the tag numbers correspond. The tag numbers are what you use to check it once you know which block to go to inside the cache, and then you can check and see if you're at the right if you have the right block. The byte offsets do not matter. You just need to know the byte offsets to indicate where your sets and tags start. So if you say you have byte offsets of 4, then you know that the first 2 bytes you don't want to look at them. You want to look at the how many set numbers there are after that. So and then after the set numbers you want to know how many tags you can use. So that's very good. But also, so you can see kind of a problem here that if I put in a lot of things with the same set, I'm going to get a lot of misses and just only fill up this space and only fill up this one space when I really should be filling up all the spaces. And so what I want to do here is I actually want to implement another kind of different cache, and that is going to be called a set associative cache. So a set associative cache, what it does is it has multiple blocks for each set. So let me kind of show that for you. So like let's imagine I have 4 sets, but they each can contain 2 blocks. So I have 1, 2, 3, and then 3. And then 4. So my blocks can take up each a different one every time. So what I'm going to do here, so what I do now is, let's say I insert again a different block, the same set with a block. So I'm going to do 0, 1 this time. I then again look in my same set and I see that this doesn't exist, but instead of getting rid of this, I now have 2 spaces to store my sets, to store my memory location. So I'm going to do that. So I'm going to put that here. And the genius of this is that, let's say I wanted to look this up. I want to look this one up or this one up. Then what I do is I simply look through the designated section. So I look through this one and I look through this one. And so I would look to see, I would check both of those, or I would check until I found one. So I could check twice, or depending on my size, I would keep on checking until I found it. If I did found it, I would return that and I wouldn't have to go to the disk, which would be great. And so that's what's really awesome about set associative. You can set more parts to check, which is really cool, and that decreases the hit rate, as you see. And so you can have multiple different sets. So I could make this 3 set associative, which is essentially 3 places to check, 4 set, 5 set, 16 set, and so that's pretty cool. And then there's also fully associative. And fully associative, what it does is, in fully associative, there are no sections at all. So I guess you think of direct map as everything's one section of one block. Fully associative, everything is one section, and everything is checked. The whole cache is checked for a block. So for instance, if I had 0101, 0101, so if I added this, I would just put it here. I wouldn't really care, and then say, okay, now I have them disk, and if I added something else, it could be anything, it could be all ones, and then I would put it there, and then if I added all zeros, I would put it there, and then let's say I wanted to search for one of them. If I wanted to search for one of them, I would simply go throughout the whole array. I would go all the way down if I wanted to find it, or until I reached the end, and then that would tell me if it was there or not. And let's say I didn't find it. The policy you usually use is called the least recently used policy, and the least recently used policy gets rid of the last thing used in the cache, so the last accessed element in the cache, which you can keep track of through bits or some kind of counting form. You don't really have to worry about it, it's just something to think about. You don't have to really worry about how it's implemented. So that's what fully associative, and fully associative does reduce the misses by the most. So we kind of saw the 2 biggest sides, but fully associative kind of has the downsides in that it's the caches can get really huge because you're storing everything. To do all this checking, that can kind of be the drawback, to check all those cases in a fast manner. So fully associative is really cool. And so the last thing I want to end on is the fact that you can possibly have is that what happens when I start my computer. and this is all blank. So when I start my computer, imagine the cache is now completely blank. It's just a huge box. It's just a huge box. Well, imagine if the cache, it can't just have nothing in it. It needs to have something in it, so it just gets initialized to random values. And let's say by chance these random values are what I'm looking for. But these random values may not actually mean anything. They may not have actually stored anything. So what we do in a cache is something also is added in a cache, and it's called a valid bit. And a valid bit is something that says the information in this bit is valid. It is something that says that, okay, the information that I have here is looked up, and I know that it has actually been used in this computer, and it's not some dummy value that's been put in there by the computer. And so, like, if I first turned on my computer, the valid bit would be 0 because none of the data is valid in the cache. And so, if I go to check that, I'm going to check if the tag numbers are the same and if the valid bit is the same, or the valid bit's turned on, because if the valid bit's turned on, then I know that that's valid data, and if it's turned off, then I know I can replace it, even though they're the same thing, because I need but then I can turn the valid bit on. So the valid bit is also something else you need to keep track of the cache. Post your comments below, guys. This is a long video. If you have any questions or you just think it's bad, have a great day.